Hello everyone, let's resume where we left off. Okay, if exothermic reactions are reactions that give off heat to the surroundings, then endothermic must be the opposite, right? Because it sounds like you have one thing going this way and another thing going the other way. So endothermic means inside. So in this case, we're going to say heat is being absorbed. So reactions that gain or absorb heat from the surroundings. So that's why if you ever have a cold pack, and you activate it, it usually has ammonium chloride, and when you dissolve ammonium chloride in water, it's an endothermic reaction. So what you feel is actually heat being absorbed from the surroundings, and going into the chemical reaction. So you ever seen a chemical reaction where suddenly things got really cold? That's an endothermic reaction. So heat is absorbed from the surroundings. Okay. So the heat given off or absorbed in a chemical reaction at constant pressure is known as the enthalpy of reaction. And we call it delta H reaction. Okay, so RWN, in case anyone is confused by this term, this means reaction. Shorthand for reaction, okay? All right. So let's go, now let's go into a little more depth about exothermic and endothermic reactions. All right. So when a reaction gives off heat to the surrounding, the energy of the system decreases. So what this means that the enthalpy of the system also decreases. So we characterize exothermic reactions by negative delta G. So delta H, sorry, not delta G, delta H. Delta H is less than 0. Okay, so negative delta H values. For example, let's say we have a balloon filled with hydrogen gas is ignited in the presence of oxygen. The reaction is accompanied by a large ball of fire and a loud boom. So you're going to generate a lot of heat, and a lot of energy is going to be expelled to the environment or to the surroundings. So what we can say is that first we have two reactants that are not very reactive right now. But when we ignite it, it's going to give off a lot of energy in the form of heat and light. Okay? So we're going to go down in energy because we're giving off heat. And then what we get is 2 H2O molecules. So we see here that the energies of the reactant and the product are very different. They're at a higher energy for the reactants versus a lower energy for the products. So if we were to write this axis here as energy, let's put this as energy, right? We see here that water has lower energy here, and that the result delta H of reaction is delta H is the difference between the initial state, which is the hydrogen and oxygen gas, and the formation of water. So our delta H is negative 483.64 kilojoules per mole. And we're going to say like mole reaction means like If I had a mole of reaction, that means 2 moles of hydrogen reacts with 1 mole of oxygen to give 2 moles of water. So that's what mole of reaction means. You're just taking the coefficients for the chemical reaction and saying, if I did this reaction once, what are the mole ratios for the reactants and products? Okay, so that's an exothermic reaction. So very, very, very exothermic, right? So so this may seem kind of familiar, right? Because okay, so can we directly take hydrogen and use that in our engines? The answer is yes. The issue with that is I think there's some feasibility issues. I'm actually not sure at all. All I know is that there has been development of a combustion engine that takes in hydrogen, so like a hydrogen fuel cell. So it speaks to that. It uses hydrogen instead of gasoline to generate oxygen. So this will actually be pretty great. But I think the issue is it doesn't supply enough energy, and I don't think hydrogen is nearly as cheap as like octane or oxygen gas. But it's a valuable option. It's definitely something that should be worth considering. Yes, hydrogen and oxygen they will explode. It's very dangerous to be close to these gases and igniting them because it can result in very serious injury. So there's also always some safety risks associated with these types of things, right? So, but in terms of energy, that'll be pretty cool because you'd be generating water, so you could replace the water in the atmosphere, and then you wouldn't be generating any more CO2. Okay, just something to think about. All right, let's go to another example now, endothermic reactions. So endothermic reactions, they take in heat from the surroundings, so they absorb heat. So these are what like coolants do. They when coolants like when you put coolant in like your AC or your car, what they do is they absorb heat from the surroundings and they can be used to cool your system, right? Okay, so in this case, if heat is being removed from the surroundings, that means heat is entering into the system. So that means enthalpy is increasing. So endothermic reactions are the opposite of exothermic. They have positive delta H values. So I keep saying delta G. I'm so used to Gibbs free energy because I'm a chemist, and when I did my PhD work calculations, like quantum mechanics calculations, I always use delta G values to determine if a reaction was feasible or not based on its activation parameters. But that's a story for another day. Okay. Oh, I don't think I filled this out over here. So let's say delta H is negative. Okay, in this case, delta H is positive. All right. Okay, so now before we go to the example I included in the slides, let's take a moment and explain what's an exothermic process. Endothermic. So if we take a reaction and one direction is exothermic, the other direction by default has to be endothermic. So let's take the example we just did. So we have 2 water molecules. Say we want to split water into its elements, okay? So I think this is a interesting field to reduce energy just because now I think this might be related to the fuel cell. Like you're trying to generate hydrogen gas and oxygen gas from water by splitting water into its elements. And that's usually very hard to do because your products are higher in energy, as I'm drawing right now, than your reactant. So it makes it hard to do this reaction without what we say a catalyst. So a catalyst is a chemical substance that makes your reaction go faster by providing some alternate pathway that is lower in energy. So it takes less energy to start the reaction. Okay, but in this case, as we look at our energy here, we draw our energy axis here. It takes a lot of energy to go from the reactants to the product. So in this case, the delta H is simply the opposite sign, but has the same magnitude of energy. So in this case, we need to put in 483.64 kilojoules per mole of reaction. So if you don't have a catalyst here, so usually when we split water, we use something called a photo catalyst. So you use a catalyst that uses light to help, or electricity, or we call it photo catalyst or photo redox catalyst. It uses either light or electricity to help make this reaction go faster. So without a catalyst, you can't really split water into hydrogen gas and oxygen. You usually need an external source of energy, either you can't even do it with heat, but like electricity, right? So we can split water into its gases using electricity, and that's a redox reaction. Okay, so you see here, it's very unfavorable for this reaction to occur. We need to put in a lot of energy. All right. Okay. So here's a here's a practical example where the reaction is fast and spontaneous. So spontaneous mean, well, I wouldn't say fast, but the reaction is likely to occur. So, or go. It's favorable to happen. That's what spontaneous means. It doesn't tell you anything about the speed or how fast it'll be. But that's the discussion that we won't even cover here. Okay? So for example, we have the reaction between ammonium diisocyanate and barium hydroxide. So this is a spontaneous endothermic reaction because the reaction absorbs so much heat from its surroundings that if your beaker has some moisture around it, it can freeze it. It can freeze it and potentially get it stuck to, like, say, the surface if it's like if it has some affinity for water. In this case, wood is composed of cellulose. Cellulose is a sugar, and it has a high affinity for water. So that's why, you know, when you pour water, when you water trees and plants, the roots, you know, usually the trunk of the tree is made of cellulose, and it loves water, so it'll absorb it very rapidly, and that's how pretty much the cells of trees get water, is that it's composed of cellulose. Cellulose can combine with other molecules of cellulose, and they form these networks of small tubes, and that allows water to travel up the tree against gravity. So that's called capillary action. Okay? All right, so that's an example of an endothermic reaction. All right, let's move on here. Okay. So give me some space. I guess I didn't need it. All right. Oh, okay. So let's do this example here. The change in enthalpy of the system that occurs when the following reaction here occurs at 298 Kelvin. Well, that's a bunch of words that I probably didn't put there. So it's an exothermic reaction. It's negative 92.2 kilojoules per mole. Okay, so for every 1 mole of nitrogen with 3 moles of hydrogen, we get 2 moles of ammonia gas. So that's called I think that's the synthesis reaction, or the basis of the Haber process, where we make ammonia. All right. So this value of delta H, it corresponds to this reaction above, where you have 1 mole of nitrogen gas reacts with 3 moles of hydrogen to produce 2 moles of ammonia. Okay. So if you don't use that much of nitrogen, ammonia, or hydrogen, you're not going to get all that energy. So usually, you know, we don't work on such scales. Like sometimes we use 2 moles, 3 moles, or, you know, twice the amount of moles of nitrogen, or 10 times the amount, or 10 times less. So this energy value is actually a conversion factor. So you can use this as a conversion factor to determine how much energy a process consumes or releases, and that's based on how many moles you have. Okay, so what would be the change in enthalpy if 2.2 moles of nitrogen reacts with 0.6 moles of hydrogen to form 0.4 moles of ammonia? So we can do this by setting up our dimensional analysis. Okay, so setting up a dimensional analysis problem. Okay, so now we can connect energy with the balanced chemical equation. So we know that for every 0.2 moles of nitrogen, and based on the chemical reaction, right, for every mole of nitrogen, right, so let's set up our dimensional analysis right here. 1 mole of nitrogen, so the moles of nitrogen will cancel out. And for every mole of nitrogen, we get negative 92.2 kilojoules per mole. So you see here we put kilojoules per mole of nitrogen. And we can say mole of nitrogen because if we look at the chemical equation, it's only 1 mole in the balanced chemical equation, right? So we just put 1 mole. And so we only took 0.2 moles of nitrogen, so that's about 1/5 of nitrogen. So we get approximately 1/5 the value of energy. Okay, there we go. Now, if we have hydrogen here, so notice for each of these compounds or species in the chemical reaction, we simply divided everything by let's see, 5? Yeah, we divided everything by 5. Okay, so 3 divided by 5 is 60% or 0.6. 2 divided by 5 is 40% or 0.4. And then 1 divided by 5 is 5%, not 5%, 20% or 0.2. Okay, so the same kind of energy goes here, 92.2 kilojoules. And then for every 3 moles of hydrogen, because that's how many moles are in the balanced chemical equation, or the number in front of the hydrogen. So this will cancel here, and if we calculate this, we see we get the same amount of energy here. Here we go. Okay, and lastly, 0.4 moles of ammonia. So for every 2 moles of ammonia, we get the same amount of energy for delta H. So 2 moles ammonia. You see here, we still get the same amount of energy because we simply reduced the balanced chemical equation by a ratio for all the species. So we get the same energy because we're just multiplying by a factor. Okay? Factor of 5, 1/5 the energy. Okay, so that's how we use thermochemistry now in chemical reactions. So if we have a certain amount of moles of a species of a chemical compound in a chemical reaction, we can figure out how much energy is released based on the value and using what we basically call stoichiometry. All right, so let's go to the next problem here. All right, now let's do a different example. We have pentagon. So sorry, that's not pentagon. I forgot to change this again. So I had this mistake last semester, but I forgot to change it. So I'm so sorry. Pentaborane. That's what the compound's called. It's not pentagon. There's a compound that looks like a pentagon, but we don't call it that. But I won't talk about it here. Okay. So pentaborane was once considered as a potential rocket fuel, and that's because it releases a lot of gas molecules. And as we see here, at 25 degrees, the change in enthalpy for the reaction is a whopping negative 8,686.6 kilojoules per mole. That's a lot of sixes there. And so that's a lot of energy. So right now, rocket fuel is, well, I don't know about nowadays, but usually in like space rockets or rocket ships, they use, well, I don't know if they use it still, but they used to use hydrazine. And hydrazine, so that was known as rocket fuel for a long time. But I'm not sure what they use anymore. They even might use hydrogen peroxide or oxygen gas, because hydrogen peroxide, when you decompose it, it produces a lot of oxygen. So it's a good source of energy and propulsion for rockets. Okay. So this is basically a combustion reaction of pentaborane to give us this diboron species. So diboron trioxide here, and then water vapor. So, at 298 Kelvin, let's say, what's the change in enthalpy for this reaction when we have 0.6 moles of pentaborane is consumed? So, we're going to take 0.600 mole B5H9. So if we look at our balanced chemical reaction, we know that for every 2 moles of pentaborane, 2 moles of pentaborane, okay, we have 8,686.6 kilojoules released, okay? So if we were to calculate this, this would give us negative 2.606. Oh, sorry, not 2,000. So let's write 2,000 here. Kilojoules. But we need to represent this using 3 sig figs, because we only have 0.600 mole. So this will be equal to negative 2.61 times 10 to the 3rd kilojoules. Okay, so that's our final answer. Right there. I can't do this. There we go. Okay, so that's it. That's using stoichiometry now with thermochemistry. All right, now let's. Okay, so we're going to stop the video there, and then I'll continue the lecture in the next one. So I'll see everyone then.